So in the continuation of first law of thermodynamics, we're going to see we have a general substance. General substance like solid, liquid, gas. Okay, there are two types of substances. We're going to talk about that. One is solid, liquid, and gas. And specifically in gas, we have two types of gas: is ideal gas or real gas. So whenever we are talking about general substances, we are considering all those four. Okay, at constant volume, when the volume is constant, we know the heat exchange dq is measured as mc dt, where c is the specific heat capacity. So c is the specific heat capacity, and that becomes c into dt. There c is the heat capacity, then we are known as heat capacity. So that is the heat exchange we use. Now when we have a constant volume, dq at the constant volume, then the heat capacity becomes cv dt. So v is the subscript, so dq equals to cv dt, and we know this is also justifying the first law of thermodynamics, where we know du equals to dq equals to cv dt, because we know when the volume is constant, so work done becomes equals to 0, so du becomes equals to dq. And from here we can conclude that cv, heat capacity at constant volume, becomes dq by dt, and that is equals to du by dt, where u is the internal energy and du is the change in internal energy. So now if we know if dt is tending towards the 0 and the temperature difference is very low, then cv will tending to infinite, or it will be not defined. So if dt equals to 0, then cv is not defined. So here we can write the formula du, change in internal energy, equals to cv dt. So whenever we are using du, means we are writing it for reversible processes. So here du m equals to, if we using cv m dt, if we are using per mole, then it will be, the unit will be joule per mole, and here the cv unit will be joule per Kelvin per mole. So that is molar internal energy change, that will be cvm dt. Now if we have a larger amount of substance, or not per mole amount of substance, like for n moles of substance, that equation becomes du equals to n cvm dt. So this equation is valid like for solid, liquid, gas. Now in gas, ideal gas and real gas. So whenever we are validating it towards the solid and liquid, so it will be also validating towards real gas, and we may also apply ideal gas, but that is only applicable at constant volume. When the volume is constant, then we can use this formula. We may use this formula. Now, if cvm of a substance is temperature independent from temperature T1 to T2, then we may use the formula directly. Du will be equals to integral of n cv molar dt, but here we are considering that cv molar is constant from the temperature range from T1 to T2. The change in U, the internal energy will be U1 to U2. But in that case, the value of molar, that heat capacity at constant volume, should be constant over the period. then integral becomes delta u equals to n CVM dt. Now let's say the value of CVM is not constant over this period, that is changing over this period. So let's say the CVM value that depends on temperature, that is equals to A plus BT plus CT square. So the case we are considering that the value of CVM is not constant during the temperature range from T1 to T2. And the relation, we consider this is the relation where A, B, C are the constant. So now when we will be putting the value of CVM, okay, we are putting that value over here. Now the formula we are getting, that is the formula. Now in that case we have to integrate that. So when the value of CVM is constant over the period, you may directly use this formula. Now when it is not constant over the period, then put the value of CVM and get the value accordingly. So now we are considering that the internal energy is the function of temperature and volume also. So du equals to partial differentiation of u with temperature and the constant volume multiplied by dt, and del u by del v constant temperature multiplied by delta v. So this is the partial differential form. First we have to keep the temperature constant, then we have to differentiate that, then we have to keep the volume constant, then differentiate that. So for an ideal gas, we found that the u, the internal energy, is the change of function of temperature only. The internal energy is the function of temperature only. So now if we try to get the value of du by dv at constant temperature is 0. So we know that when the temperature is not changing, so the delta u, it has a term of dt. So it includes the term of dt. So when temperature is constant, that value is 0. So del u equals to n CV dt. So the formula we get is n CV dt. So now if we talk about molar internal energy change, if we have a numerous amount of moles not equals to 1 mole, then the formula of molar internal energy change will be CVM dt. Now if we have the n moles of ideal gas, then the formula we will be using will be du equals to n CV dt. So this is important formula and it is always applicable. So whenever we want to calculate the change in internal energy of n moles, and the CVM is the molar internal energy and constant volume, and dt is the change in temperature. So that formula of change in internal energy we may always use. Now if we talk about for general substance like solid, liquids and real gas, so in that case the du by dv, that is not equals to 0. We have seen in case of ideal gas it was 0, but when we talk about the general substance, the substance which exists in real, so in that case that is not 0. So for a real gas, du by dt may be positive or negative, and at constant volume du by dt is 0. So for real gas at constant temperature, in case of gas expansion, we know distance between gas molecule increases when temperature is constant and gas is expanding. So the distance between gas molecule is increasing. So in that case, if attraction force is dominating and attraction force decreases, in that case attraction force decreases, and that potential energy will increase. So internal energy will increase and du change in internal energy will be positive. So that term we will be putting as a positive. In that case, if repulsion force dominates, then we know repulsion force if decreasing, the repulsion force is decreasing, the potential energy will be decreasing and internal energy will be decreasing. In that case, u final minus u initial will be negative over here. So that term will be negative in case of we are talking about real gas. So in case of gas compression, distance between gas molecule decreases. So whenever we are compressing a gas, the distance between those gas molecule is decreasing. So if repulsion force is dominating and repulsion force is increasing, so potential energy will also increase of the system, and internal energy of the system will also increase. So U final minus U initial will be positive. So in that case, du by dv, because the compression is there, so dv is negative. So if du is positive, dv is negative, we are taking it as a overall negative term. Now in that case, if attraction force dominates and attraction force is increasing, the potential energy is decreasing, internal energy is decreasing, and du is negative. But hence we are compressing the gas. So in that case, dv will also be negative. So that negative and negative together making a positive. In that previous case also, the dv, in case of expansion, dv is always positive here. So the sign convention is according to du. Now as we know that internal energy is inversely proportional to minus 1 by r, that we have seen already whenever we are talking about internal energy between two molecules, that is always inversely proportional to minus 1 by r. So when attraction force is, when we are talking about the gas expansion, the molecules are going further to each other. In that case, if attraction force is dominating, means they are trying to attract each other, and the attraction force is increasing, so means they are moving towards from far from each other. In that case, we know the value of 1 by r, the value of r is increasing and the value of 1 by r is decreasing. Now if we talk about the negative of 1 by r, so it is going closer to 0. As the particles are moving further to each other, the r is increasing and 1 by r is decreasing, and negative of 1 by r is increasing. Why? Because it is going towards the 0. So that's why the internal energy increasing here, and that's why the internal energy is decreasing here. Similarly, if we can see the sign convention of internal energy in case of gas compression. So that's how the various cases of first law of thermodynamics we are considering here. Now for the first law of thermodynamics for solid, liquid, gas. In case of gas also, when it is ideal gas and when it is a real gas, how we will be dealing the internal energy and all the thermodynamical term.